All right, folks, it's Bass Action back in action here. In this video, we are going to look at a special triangle that comes up often in mathematics called a 30, 60, 90 triangle. It's not very creatively named because it's simply named based on the angle measures in the triangle. The triangle will have 30 degrees, a 60 degrees, and a 90 degrees. This is going to give us a shortcut and a fast way to find measures in triangles when you know that the angles are 30, 60, and 90. Now, to find that quick short pattern, we're going to do a little proof here that's important for you to remember and understand. We're going to start here with an equilateral triangle. So I'm telling you that this triangle is equilateral, which means this angle down here in the bottom right is 60 degrees. Of course, this one over here is 60 degrees as well. And you can see that we've drawn in the height of the triangle, which we remember from last semester is going to bisect that angle and make this top angle 30 degrees. Since we've done that, then what we can have here is we can focus on one of the triangles. I'm going to look at the one on the right, and we can see that that triangle now is a 30, 60, 90 triangle. So what I want to understand is and get is an expression for each side in the triangle in terms of x. Since the triangle was equilateral to begin with, I can definitely fill in this side of the triangle immediately as a 2x, because by definition we made the two parts down here each x. Now what we need to do is we need to get a replacement. We need to be able to substitute this value for a. So we're going to do a little Pythagorean theorem here. So I'll have a 2x quantity squared equals my a squared plus my x squared. Again, we're just working on that highlighted triangle. So I'll have a 4x squared equals my a squared plus my x squared. Moving the x squared over, a 3x squared equals a squared. Now we're just going to do our square root of each side. So then we'll have our a equals, now this is an algebra property that you need to remember. If under the radical we have two values that are being multiplied, we can write them as their two separate terms. So I will end up with a square root of 3 times an x. What that's going to allow me to do then is replace this with the square root of 3 times x, and that will then give me a coefficient here, and a coefficient here. And we've talked about extended ratios before, so now I'm going to write these three coefficients as an extended ratio for any 30, 60, 90 triangle. And I can write that as a 1, and I'm going to use it with the colon style, then I'm going to do another colon over here, and 2, and a square root of 3. And by writing them in that order, I have them now in their increasing order. The 1 represents the short leg, the square root of 3 represents the long leg, and the 2 will represent the hypotenuse. Now, if you flip to the inside of the foldable, we're going to look at some examples here. So we're going to just do a couple examples here thinking through how to do this. And I'm going to rewrite that extended ratio, that 1, that radical 3, and the 2. And when we move in the right direction, we are going to multiply. And if we go in the opposite direction, we'll divide. Okay, if we go from right to left, then we'll divide. So in this first problem, you can see that I've given you this 4 square root of 3. This is across from the 30 degrees, so this is going to be called our short leg. Now, I used that language in the previous page in our little proof, but now we're going to see how this really gets applied. This has to be the short leg because it's across from the smallest angle. So this is going to be our short. If I want to go from the short to the long, my long, of course, is right here because this angle would be 60. So if I'm going from the short to the long, I just need to multiply by a radical 3. So I'm going to take my 4 radical 3, I'm going to multiply it by a radical 3, which means I really just have 4 times 3, or 12. If I want to go from the short to the hypotenuse, again, I'm starting here on the short. This is going to be my hypotenuse. When I look at my extended ratio, I'm going to start here, but now I want to go all the way to the 2. So I just multiply by 2. So this is going to be an 8 radical 3. No long work that I need to do at all. On this next one, I have an equilateral triangle here, and you can see that I've bisected one of the angles, which makes this little angle right there 30 degrees. And again, I gave the short. So if we want to find a length of one side in the triangle, I want to get to this little piece right here first, which would be the long, particularly in this little baby triangle right here. All right. And we're going to use this picture later in the semester, so that's why I've got it here in our notes. So if I want to go, again, from a short to a long, same thing as I did here, I'm just going to multiply by this radical 3. So I'm going to take my 21 times my radical 3 to get this little piece. So this will become a 21 radical 3. Then, of course, this is 21 radical 3. So the whole side, add them together, is going to be 42 radical 3 units. Now on this next problem, I'm missing a number, so your printout might have the number on there. I've probably fixed it for some of you by now, but if not, we're going to go ahead and we're going to fill in a 21 right there. Now, I've got a hexagon here, and I'm going to tell you this is a regular hexagon. And if you haven't studied regular hexagons yet, what you can do is you can probably remember from your elementary or middle school days playing with pattern blocks that hexagons are really made up of 6 equilateral triangles. So if a hexagon is made up of 6 equilateral triangles, then this angle down here had to be, this little one right here has to be one angle in the equilateral triangle. So together it was 120. That means that this little one right there is 60 degrees. And again, I'm going to focus on what I'm going to call this little baby triangle, this little one right here. We want to get to the perimeter, and in order to get to the perimeter, we need to go from the 21 where we are to this little piece first. This time you can see that I've given you the long leg because this 21 is across from the 60 degrees. So now I have the long, and I need to get to this short leg. So now I'm going to go from the long to the short. And if I'm going from the long to the short, I need to get smaller. And when I look at my extended ratios, that means I'm starting here and I'm going backwards. That's why I'm dividing. I'm getting smaller. So I'm going to take my 21, I'm going to divide by the radical 3, and now I need to rationalize. It's kind of an old school mathematics thing, but we're going to rationalize multiplying top and bottom by that radical 3. That's going to give us a 21 radical 3 over 3. And then, of course, algebraically, we can reduce the 21 over 3. So that's going to get us for that little piece here of a 7 radical 3. Now, that's just the little piece, which means the whole side in the hexagon is going to be a 14 radical 3. And, of course, I want to multiply that by 6 to get my complete perimeter. So 14 radical 3 times 6 is going to give me an 84 radical 3. Okay, now the last one that we're going to do is we're going to look at another equilateral triangle. This one is going to start you off with a side length of 22. So this is essentially the proof that we had on the previous page, and we want to get to the height. So if the one side is 22, I'm going to draw in the height. I know that when I draw in the height, it's going to bisect that side, so it's going to make that 11. I know this bottom angle is 60 degrees. So now I'm just going from the short, because that would be my little short, to the height, and the height is going to be the long. So I just need to multiply by the radical 3. So that height is going to be 11 radical 3. All right, when you get in class, we'll do some more examples, but the most important thing right now is to get that extended ratio in your head and understand where it came from.